Okay, so we're gonna have to go back to the alt setup for one video because I had to kind of give up my screen for tonight. And I hope the audio is gonna be fine as well. I'm somewhere else, but it should be fine. Cool. And actually, I just wanted to use the chance to explain a little bit what I kind of been thinking about in the past couple hours, because I just realized that like what we're doing here really it's really similar to VQE, right? Because at the end of the day, like I was totally lost, but I just tweeted this a couple hours ago. I kind of realized that that really the MPS is actually it's actually the quantum state, right? Um, mm, 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 where was that? That was a paragraph, I think. So notice how so here this is introduced as in like P is the level of the system. So you kind of have two levels in a normal quantum computer, right? Like a 0 and 1, two levels. So for all the speeds, right? Like n is the number of qubits, and so you kind of have really a rank n tensor, which is what I was kind of suspecting last time. Like I know you usually write in the standard that you see in terms of circuitry in quantum computing stuff is that you see just like a big array with all, like for example, you have 3 qubits, like you just see, you know, a complete array with like all the 8 possibilities in an array, and you use the column array, or you use that like, yeah, basically that not the ket, exactly, that ket as a way to represent the state, but like you can essentially do that as well in a like in form of like an n, a rank n tensor, where literally like you use, let me see if I can open Anaconda. So actually let's go to workspace, and let's go to workflow optimization and start Jupyter, because I wanted to kind of play a bit with the code here. But essentially each index of the tensor is kind of makes reference to one to a qubit, and actually kind of have two components, right? It will have the not this one. It will have a component for, because I was playing with these. It will have a component for maybe this is what the components mean here. So we'll have the component for, let's say, if this is my matrix, right? Like it's gonna have, if we have 3 qubits, you're gonna have the 3 indices, right? So you know these would be qubits 0, right? If we index them like that. Let me comment these, right? And so on and so forth. So you know this would be like, and I think it's the, hold a second, it's the amplitude of no, is it? I don't think that's, and that's gonna be, is this gonna be an amplitude? I think so. So you have 3 qubits and then you kind of index them like that. I think that's the trick, right? So that kind of, it was confusing because it moves away from the standard way of representing circuits, right? So that's what you're saying. These are the coefficients of each of the, you know, this I1, I2 until IN. Those are the kind of the computational bases, right? For your n qubit state, exactly. And so it's basically saying that it's going to have p to the n numbers, and this is a complex number. It's the actual amplitude. Describe the wave function psi, and then can be understood as the coefficients of a tensor C with n indices, exactly, where each of the indices can take up to p different values. Yeah. So basically, because that's kind of it's the level, right? So that makes sense. Cool. And then I kind of realized that I think what you're doing, if I was reading this well, because it's like a optimization of the first bond. So to optimize the first bond tensor, a range of procedures can be used. But amongst the most effective are iterative algorithms such as Davidson or Langso's algorithms. So what are these algorithms? Langso's. Let's see. What is this doing? It's a direct algorithm devised by Langso's adaptation of power methods to find the m most useful eigenvalues and eigenvectors of an n by n Hermitian matrix. Maybe I'm a bit wrong. I'm not so sure. I thought what you were doing is because there's I had the impression I read before, like yesterday, that there was some kind of variational part to these. Two neighboring MPS tensors at a time to this performed using iterative eigensolver approach. Before the next step, single tensors factorized using SVT or density matrix composition to restore the MPS form. The bond dimension can be adapted. But like, what's the starting point, right? Like, because even these is like, for the algorithm to be efficient, H must have some simplifying properties. For example, H could be the sum of local terms. And this is, I think, the same that you kind of find with VQE, where if you're Hamiltonian, if it can be decomposed, like, so there's a limitation, yeah, so if the Hamiltonians can be constructed as a sum of Pauli operators, then, and their tensor products, then, for example, we can have the following Hamiltonian, right? So that's exactly the same idea, right? You measure for each component, and then you add the results up. And I think that's exactly the same that is being explained here. If your Hamiltonian is just a sum of tensor products of things, it's a sum of, basically, of smaller tensors, then, yeah, it's an NPO tensor network. And so, and here's like the NPO is an actual matrix product operator. So, and that kind of, I think, confirms what I was suspecting, that this is going to be, this is actually going to be, like, MPS is really just a state, and that's an operator. And but let's try to, okay, so I don't know if I explained myself really well, to be honest, but I think that those thoughts clarified a bit the next steps. But I want to really get started with these. I don't even know, like, I was aiming to start with step 0, but I got a bit lost, and I'm trying to understand it more. So before you begin with the MRG, it's imperative to bring the initial MPS into an orthogonal form. But what's the initial MPS? Like, because that's what you would, you would just start with a random one or something. That's what you would do with VQE, right? You start with a random ansatz, and then you optimize the ansatz so that you kind of minimize the eigenvalue, you minimize the expectation value, and so you kind of both find the eigenvalue and the eigenvector. Maybe I should just read farther here. So, is DMRG explained somewhere? So the phenomenon is probably the most famous example of T states because it is behind some very powerful methods to simulate one-dimensional quantum many-body systems, most prominently density measurement. It's referenced in here. It's also behind other well-known methods, just blah, 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 blah. Okay, so where is this mentioned? Here. This is an algorithm from 1992. That's nuts. I doubt this is going to be accessible. I bet that's paid access. PDF. Yeah. Whatever. I really have to figure it out then. Maybe this will just be the very first easy, accessible tutorial out there. finding ground states, variational optimization, and maybe it's explained here. That's variational optimization, but it's not the MRG. No, a few remarks are in there. First, if we perform this optimization for an MPS with open boundary conditions, then what we recover is nothing but the famous tensor generalization group algorithm and the language of MPS. This is particularly appealing since using the MPS picture it also... Okay, so basically it is really given a Hamiltonian H, the variational principle states that for a given quantum state psi, it will always be the case that blah blah blah, and so the expectation value basically. Therefore, if psi is a tensor network belonging to some family of states, like an MPS or a PEPS, then with a fixed bond dimension, we can always approach the ground state energy from above by minimizing this expectation value over the relevant family. Where by family we mean either MPS or PA or PEPS or any other family of Tn state with bond dimension D, and where lambda is a Lagrange multiplier that introduces the constraint that psi must have norm 1. Oh, this Lagrange thingy again. Ideally, the above minimization should not be done simultaneously over all the free parameters of the tensor network state, exactly. Hence, over all the coefficients of all the tensors for all sites. However, this is normally quite difficult to implement and not particularly efficient. Instead, is to proceed tensor by tensor. This is to minimize with respect to one tensor while keeping the others fixed, then move to another tensor and repeat the minimization and so on. In practice, one sweeps over all the tensors several times until the desired convergence in expectation values is attained. The way to minimize with respect to one tensor works as follows. Imagine that we fixed all the tensors in the Tn except one of them, which we call A. The coefficients, and that's what's gonna that's gonna be that's your ansatz. The coefficient, I mean, that's the way you're, so that's the one you're kind of going to be optimizing. It's pretty smart. So you're going to fix the rest. The coefficients of A are now our variational parameters. Okay, so and yeah, because the tensor will probably just be the small tensor will just be of dimension 2, so it's going to be it's just going to be like a 2 by 2 matrix, probably, right? Then the minimization is written like this. In the above equation, it's just a tensor, but it's just a tensor A, but with all its coefficients arranged as a vector. So this is like, yeah, so you're reshaping the whole thing so you can calculate these. What is HF? Do I have to have this Lagrangian thing in here? So those correspond to the tensor networks for these and for these, but without tensors A and A. That is the environment of tensors A and but written in matrix form. So you... oh god. This minimization can be done like that, so whatever minimizer you put in there, which leads to the generalized eigenvalue problem. Numerically by using standard linear algebra packages, and to calculate both HF and N, one must use the tools explained in the previous section to compute expectation values. And to calculate both HF and N, one must use the tools explained in the previous section to compute expectation values of physical observables and effective environments in a TN. In practice, this means that both HF and N can be computed efficiently and exactly for an MPS, whereas for a PEPS, this calculation is also efficient, but if we perform the optimization for an MPS with open boundary conditions, then what we'll recover is nothing but the famous density matrix normalization group algorithm. Yeah, so this is the MRG, essentially. a tensor can be transformed into a vector by moving and grouping its indices. Yeah. Fancy. Okay, I get it. Proceed to get the normalization matrix N. So what this is saying literally is like, you know, so you're optimizing tensor by tensor, like the small tensors. So these are fixed, I guess. That's why they are squared. Or was it the... Okay, or this is this right orthogonality thing. I can interpret the MPS tensor numbers collected as a change of basis from the basis in the bond index like that. This interpretation motivates transforming the matrix H into the following diagram. If we take H to be an MPO form, we can compute the transformation efficiently, defining the RJ tensors along the way. For efficiency, it is crucial that the edge tensors be created by contracting each MPS or MPO tensor one at a time in a certain order as follows. Next, combine the first two MPS tensors by contracting over the shared bond index. So you have these. At this point, it's hard to observe that the bond tensor does not contain just partial information with the tensor represented by the MPS. Rather, it is the entire tensor eigenvector of H, just written in the basis. If the alpha 2 basis spans the subspace of the whatever represent eigenvector of H, we seek the mathematical eigenvector. I don't understand this. Okay. To optimize the first bond tensor, a range of procedures can be used. For example, gradient descent, or conjugate gradient. We're going to stick with gradient descent. But among the most effective are iterative algorithms, such as Davidson and Lang's algorithms. So okay, we'll just stick with gradient descent. The key step of each of these algorithms is the multiplication of B12 by the transform matrix H, using the projected form of H in terms of RJ tensors defined above. I'm getting lost even with the diagrams, I think. So what this means is what I guess is we have to come up like with we should really try a small example, right? So let's try a small example. Insert cell below. We want to find the lowest eigenvalue of like a simple matrix. Damn it, I mean, we could even use these. Okay. We could even use these. So let's use Masty Thoughts example. So let's imagine this is a Hamiltonian. There's only one qubit. Okay. So the Hamiltonian is 2 times z plus x plus I. It is the following matrix. So this is our Hamiltonian. Cool. Let's do this. So how do I even start? I got NumPy. So our Hamiltonian is basically array of like, what did I say it was? 3, 1, and y minus 1. Okay. 1 minus 1. Is it not defined? I'm going to keep these things just in case. And now what? Still running? Yeah. That's nothing. It's just like that? No. What is the syntax? Why isn't this working? Oh, there you go. So this is age. Cool. Now it's just one qubit, right? So basically, but if it's just one qubit, that should be actually fairly simple. I wanted to kind of have two maybe qubits. Will one qubit be illustrative enough? So if I take one qubit and that's the Hamiltonian, and now I want to have so sort of basically the MPS, right? So the MPS is just really, in this case, one tensor, isn't it? I want to have two qubits. I really want to have two qubits. So how can I make up an example? Can I just make up an example? I just want to make sure that I don't do a qubit Hamiltonian, because I don't want to get like something wrong in here, or a matrix where this wouldn't make any sense. I think in the VQLS qubit Hamiltonians. So these are some lectures actually. I just want to have an example. I should read this probably. That actually seems quite useful. Let me bookmark this. Let's just, I don't know. Let's just make up like, or what if I just kind of like have basically the same, but like somehow, is that a valid Hamiltonian? And now I basically kind of copy the same, but like with the zeros here. I guess that should be a valid one because it's kind of taking the same thing here and then just having zeros in the other places. I don't know. 0, 0, -1, and then 1, -1. Okay, so you kind of have these now. Whatever. Whether this is correct or not, we'll see. So we have 2 qubits, and now basically we would have, like, we kind of should have the MPS kind of basically have to be 2 tensors. So what I could do is I could actually use these functions, right? Because this is, okay, so this create tensor of dimensions and rank. What is the difference? Dimensions. What are the dimensions then here? Create tensor. Create a block. Construct new matrix for the MPS with random numbers from 0 to 1. I know that just creates tensor with random integers. What is dimension 4 though? Okay, I think we don't need these. So we can, I think, but what is dimension used for here? Dimensions. For dimensions 2 to 40. So it creates a tuple dimensions least. It's just the name of the dimensions, right? But it's kind of I don't really. Memory cost. Whatever. Cell. I feel like I should understand this, but I also feel like I don't want to waste time with this. Dimension, and then sample dimensions list. What is these actually? 2 by 2, 3 by 3, 4 by 4, 5 by 5. So the rank, the dimensions is the P, I guess. So that's rank 2, but then it's like the actual dimensions. Okay, I get it. Yeah, but this is not needed. So cell, edit, delete cells. Cool. So what we do here is we create a block. So this is dimensions will be 2. Create an MPS of rank 2. I guess that's what you're doing. And so it creates a block of dimension 2 with bond dimension happens. So dimensions 292, ranks 2 and 150. That's all I want to know. That's all I need to know. This is all I need to know. This is basically gonna delete this stuff. Because I've retrieved. I'm gonna keep this for a second. So let's say I want to build like an MPS of rank. So we have 2 qubits, right? So we have 2 qubits. Rank equals 2 qubits. Okay. So we have basically rank. So dim is the kind of the dimensions, right? So this is 2 as well. We're working with qubits. What is the bond dimension? I don't know. So what is the bond dimension? Where did I take this from, actually? I took it from... So let's maybe... Bond dimension, what's the first time it appears? Where is the first time it appears? It's called bond. Okay, so there are different values that each one is a quantitative measure of the amount of quantum correlations in the wave function. These new degrees of freedom, like I said, you're creating the tensor network. So as well, gluing the different DNA blocks, these new degrees of freedom are represented by the connecting indices amongst the tensors in the tensor network. The connecting indices turn out to have an important dimension. An important physical meaning, they represent the structure of the many-body entanglement in the quantum state. And the number of different values that each one of these indices can take is a quantitative, the number of different values that each of these indices can take is a quantitative measure of the amount of quantum correlations in the wave function. These are called bond-oriented indices, and the number of possible values are referred as the bond dimensions. The maximum of these values, which we called above D, is also called the bond dimension of the tensor network. To understand better how entanglement relates to the bond indices, let us give an example. Imagine you are given the tensor network with bond dimension D for all the indices and such that. Okay, well, what should be the bond dimension for a qubit? There is no entanglement is present in the wave function. Then no entanglement is present. Ah, that's interesting. So if the bond dimension is simple, indices of the tensor. So actually it seems like by design you're already kind of saying, well, the way you're going to connect these indices is you're already going to define whether there's some sort of entanglement there or not. With this maximum DT over all tensors, we assume that the rank of each tensor is bounded by a constant. The D is the bond dimension. And I think here they assumed because tensors carrying the external indices are all right orthogonal. This merged. The bond dimension can be adapted. This adaptation is optimal So the bond dimension, so that's something else you can adapt. The bond dimension or tensor train rank of the MPS can be adapted. This adaptation is optimal in the sense of preserving the distance between the network just after the optimization step in the network with the restored MPS form. So this is also something else you can actually parameterize, where you're parameterizing. This means you're basically defining the entanglement of your ansatz this way. It's a bit it's a bit difficult to grasp, I think. Oh, look, this is the typical type of ansatz that is used. This is so heavy that I'm just like too lazy to read through all of these. If d equals 1, then the upper bound says SL equals 0, so no matter the size of the block, that is, no entanglement is present in the wave function. This is a generic resolve for any Tn. If the bond dimensions are trivial, no entanglement is present in the wave function. Tn state is just a product state. This is the type of ansatz that is used in mean field theory. Second, for any d or bigger than 1, we have that the ansatz can already handle an area law for the entanglement entropy. Changing the bond dimension d modifies only the multiplicative factor of the area law. Therefore, in order to modify the scaling with L, one should change the geometric pattern of the tensor network. This is just way deeper than I thought. This means that the entanglement in the Tn is a consequence of both d, but also the geometric pattern. Oh wow, okay. Really? Okay, let's take a look at what happens if I just say bond dimension 1, no entanglement between the qubits. And so I create the MPS, and now I say MPS nodes. What do I get? So I get this node, with a dangling edge. So it's this tensor. So can I just say, so for tensor in for node in MPS nodes, print node tensor. Node. So API docs. So how do I get the tensor network? So tensor network, how do I get the actual tensor? Tn, probably I have to actually Tn, no Tn connect, Tn. What's the basic, no, don't want the reference. Okay, that was the introduction. I want to be able to paint these. Okay, so that's the bond stuff in here. So blah blah. Physical indices. The new horizontal lines are called ancillary indices, with physical ancillary indices of each side being labeled respectively. product of NPSs. No, I just want to, not these. Basically per tutorial, no, I want to get the reference documentation. Oh, that's it here actually. Tensor. I wanted to find a tensor. And I wanted to find, so get a node and get the tensor. Parameter tensor, get tensor. Get tensor. Okay, so this is then two tensors that look like that. If you grant the NPS, like these. Because when if I take a look at for edges, for edge in NPS edges, print edge. What does the edge look like actually? Bond dimension. So you're contracting. What if I just I don't want to do that. What I want to do is I want to actually doesn't print. So what's the actual length of this? Print. Oh, actually, it doesn't even go in here. So basically, there's no edges, right? Probably. 0. Why is that possible? Rank 2, so I have 2 qubits. Or isn't this the way you do it, the rank of the... Yeah, well, of course, that will not create any node in between because it will just be a rank -2. Create a new matrix for the NPS with our numbers. Build the NPS tensor. I'm confused now. So what I should create if I'm working with 2 qubits. So if I work with 3 qubits, maybe that's just like dimension 2, and then, you know, whatever, we'll just fix that. And now there's one edge. So what if I print this edge? It's a named edge, obviously. If I print the tensors, now we have, so the last tensor always looks like these. Because what you want to do is if you contract the, if you do like, if you contract the edges, this edge, and then you print an A, it's got 2 dangling edges, so 2 dimensions. Now, what is the result of it's 2 by 2? So it's a 2 qubit. Is it? I'm just struggling with the mapping, you know. That's kind of what I'm realizing, that I'm struggling with the mapping. I don't really understand how to map these. So you have break the weapon in small pieces. Maybe this will be explained. I mean, that's the part that I read. Yeah, that's the part that I already read. So figure 9 will be an empty is the number of parameters for the tensor. This is just talking about the parameters. I don't really care right now. I just want to have the replacement of tensor C by a T involves the appearance of extra degrees of freedom in the system, which are responsible for gluing the different DNA blocks together. These new degrees of freedom are represented by the connecting indices amongst the tensors in the tensor network. Yeah, that's also what I just read. Okay, so here they're going to try to understand a bit better what is this entanglement. How you understand this entanglement. That's definitely worth taking a look at. I just wanted to move forward with this small example, but I'm not really understanding what I have here. So, because I want to have 3 qubits, right? Okay, but the rank of the tensor, one dimension is 1, dimensions is 2. And if I have 2 qubits, the rank of MPS should be, what should it be? Maybe the rank of the maybe it should be 8, because at the end of the day you want to have 1, 2, 3, 4, 5, 6, 7, 8. Now then you're gonna have 3. There's 2 tensors and there's no edge connecting them. That just makes absolutely no sense. What is the rank of the NPS state? Awesome. NPS. One, two, three, four. 4 side NPS with open boundary conditions. If I want to have so build an NPS tensor. So you start with a node in here with 2 dimensions and then a 1 dimension. Then you have an actual node in between. Oh, look at these. Okay, so you're going to create a node for this is where rank is used. So if you want rank to be, yeah, that's the problem. If you want rank to be, the rank to be 2, then there's no. But in the rank to be 1, there's going to be one thing here. then to build the MPS. So okay, but there should be an edge, right? Because you go from 1 until rank -1. Okay, probably not. Connected edges. So rank just this just tells you so with 2 sides. I'm really lost. That's not what I'm looking for. It's definitely not what I'm looking for. So this gives me 2 nodes, but no edge, and that's confusing. 2 nodes, but no edge. Why? Why there's no edge? That's QB1, that's QB2. Whereas if I say rank 3, it gives me 3 nodes. And 1 edge. That is kind of confusing. Is the edge between these 2 nodes? And what is this thing here? That was this basic tutorial here, right? So we begin by creating directly the node structure of the MPS. First, we define functions to build each block, and then the MPS itself. Create MPS. Physical dimension 2 and rank 20 with 20 qubits. So if I give it rank 20, dimension 2, bond dimension 2. So what if I play with a bond dimension? Rank 2, bond dimension 2. Oh, that gives me 2 nodes. First of all, that gives me print length of MPS nodes and print the length of MPS edges. Still 0 edges. Bond dimension 2 though. So I really have to have, if I have 3 qubits, then I get 2. Why I get 1 edge? I don't understand that. I should be getting 2 edge. What is MPS edges, first of all? Actually. Connected edges. So, you create a node. Then you're creating sort of rank -2 nodes. And then the final node. And then you take connected edges. And you're connecting the 0, 1 dimensions with the 1, 0 dimension. So you're literally doing, at least you're adding one connection, right? There's a bug in here. It's not adding it. It's not adding it. Like, it's definitely not adding it. Like, I think that's the way this should look like. What am I doing? C is not defined. What have I added here? The C. That's not what I want. Okay, I don't care about these. So, what? Too many indices for array. Split cell, delete cells. Yeah, that makes sense. Okay, that makes more sense because now if I say rank 2, dimension 2, yeah, that makes sense. Okay, leave it here. I think there's a bug here. Okay, so I don't know. How can I report that? Maybe Twitter. Or is there a way from you how to contribute? So you should open a ticket or something. Code reviews. Contributor license. I have no idea. I've never contributed to this, but I think that is definitely a bug. Because you're creating the connection, but you're not adding it to the connected edges. Yeah, that's definitely a bug. Okay, but now that makes sense. And so now I have these edges and these connections. Okay, so if I take a look at if I now do for NPS, for node in NPS nodes, print node get tensors, sorry. Then I have these two tensors, and then if I do the same for the edges, I'll get the edges, right? Edge in NPS edges, print edge, edge, get tensors. Can I do this? No. Get whatever. But there's one edge, right? So that makes sense. And what do I do next? So now I have the tensor network. What is the next step of the algorithm? I got lost. So now I have the Hamiltonian, which I should kind of be able to have in this form of an MPO. How do I get? So I have my Hamiltonian. I want to have my Hamiltonian now in an MPO form. Can I get that? That doesn't even appear here, but I think that if I do matrix product states, I would kind of have to now. So by some local time zone means suggest like these So as an MPO, how do I? So here's an example. Maybe is there anything in here about MPOs? No. I don't think so. Matrix product operator example. Whatever. So this would be something expressed like that. Expectation value. That's another library though. So the next step is basically get these in MPO form. If I do, I guess if I just do like, what was the example here? I think there was an example, quick start. What is here in GitHub? If I do these basically, so if I basically do these, which I had done here, right? Finite, get tensor, blah blah blah. Left edges. So that's the way that I was doing node 0, node 1. I don't know. So so this has got 2 dimensions. If I split these, no, that's not like if I do the SV whatever. If I split these with a singular value decomposition SVD, I'm not gonna get an MPO. So I really don't know how to get an MPO. H in MPO form. That's kind of my next step. And then I can get on with the algorithm actually.